Hi everybody, thank you very much for having me. My name is Andrew Culver. I'm from Virginia Beach, Virginia. I grew up in Canada. I love visiting Japan, so I appreciate so much you having me. This is really a world-class event. This has been fantastic, and it's been a great experience. I can't wait to tell everybody about it and encourage them to come as well. So today we're going to be talking about ROM hacking with Ruby. ROM hacking has been a hobby that I've been sort of engaged with since I was a young kid, actually, before I was even really a decent programmer. It was through the hobby of ROM hacking that I learned how to program in C when I was in high school. It also was what gave me my first exposure to Japanese, hiragana and katakana, and sort of set me on a course of trying to learn some Japanese over the years as well. So it's really great. It's interesting though, because I've never presented ROM hacking before. Anytime I've ever done a talk proposal or anything like that, it's always been something businessy or codey, not necessarily fun like this. But ROM hacking is just fun. There's no business here. That would probably be illegal. And the reason for that is that when we talk about ROM hacking, what we're talking about is applying a layer of your own work, of your own creativity over something that has already been created. I think the important thing, just as a disclaimer right up front, is to sort of describe that when we work with ROM data, we're oftentimes working with data that is under copyright, that we've purchased somewhere. Like, I was tempted actually to go pick up this game at Akihabara so that I could show it to you. But it's actually on my shelf at home in Virginia. It's a game called Night Gundam Mono, does anybody remember the name of it? Mono Degami, something like that. You'll see in a second, and then you can read it. But the game that we're looking at today is a game that I have back at home. And the interesting thing in the video game life cycle is this. The typical video game life cycle for the average person is that they read about a game in a magazine that's going to be coming out at some point. And we all know that there are people, so sometimes we know them, who are working in a company to put together code and game engines and graphics and music and all of these things, and they put it all together in a package, and then they ship it to the store, and people buy it. And it is on, you might download it, but back in the old days, it was on a cartridge, right? And that cartridge was something that you purchased and you owned. You owned a license of that game that they had created. And the interesting thing about it is once you've got that cart is you'd plug it into a system which was designed to read that cart. And it would execute the code on that cartridge, on the system, and you would interact with the system, with the behaviors and the data and the graphics and the sound and all of those things, the experiences that they had built into this package. And that's the video game life cycle for most people. But we are not most people, not even close. So for us, if you're here, you're probably into video games or were at one time, but you have something else. You understand computers, and you understand data, and you understand that 6502 processor or that Z80 sound processor is something that you can work with. It's something that you can interact with. So the video game life cycle for us includes sometimes ROM hacking, because we can now take that cartridge that we've purchased and plug it into not the system, but into the computer and read the data on that cartridge and get a copy of it. And with other tools, you can rewrite that data to a new chip and attach it to the cartridge and put it in the system with whatever you've done to the data. And that's ROM hacking. That's the nature of ROM hacking. It's an extension of the video game life cycle that if you've got the skills, you can participate in. And interesting for me, it was actually my interest in ROM hacking that motivated me to develop the skills of programming. First learning how to program in C, and then going to college, and the rest of my career from there. So I want to share some ROM hacking with you. So again, we talked about behavior and assets. Behaviors and assets. And just to give you an example of this, I'm going to go over things that I've just said, but in the context of this game, Night Gundam Story 3. This is old. Has anybody played this? Somebody did? Okay. You are awesome. Because nobody in the United States has played this game. Why? Because it was never released in the United States. But it had worlds. It had places, levels, towns, cities, houses. It had fonts and dialogue. It had enemies, graphics and music, like many of the games that we play, that we love the music. It had characters, items. Those characters and those items had attributes. They were different. There were things to discover. You could progress through the game and get bigger and better characters and bigger and better items. But at the end of the day, it was all just code and data. And really, code is data too. So it's all just data. And this is the interesting thing when you get your head around it, is that cartridge had everything. There was no magical place that it was pulling other content from that was making us feel those emotions when we played the game, that made us interested, that we were having a fun time. It was all there on the chip. And now it's all there on your hard drive. So why ROM hacking? Why take it further than the game? Well, first of all, you can make games accessible. This isn't something probably a lot of people in this room would appreciate, although the other group of us who are coming in from other countries where these games didn't originate, many of us experienced not being able to play games that we were anticipating because they weren't released in our country. So with ROM hacking, you have an opportunity to make them accessible. And another thing that you really start to appreciate when you're looking at code, especially disassembly, or looking at data structures, and finally understanding the way that something works, you realize that nobody has thought about it in 25 years. They shipped it and they forgot about it. They moved on in their career. But you're reconnecting with something that maybe nobody has looked at in 25 years and appreciating it and interacting with it and having a new experience, reconnecting with the game in a new way that you can now that you couldn't when you were a kid. So why Famicom? Why NES? Why are we going to look at that? Because the early console architecture is relative to what we execute on today, really, really simple. And it's still a lot of the basic computing concepts haven't changed. So we can cover quite a bit in 30 minutes today. And a lot of the terminology will be the same as things that we talk about on x86 and other desktop processors. And the simplicity of the early consoles make them great places to learn these basics, even for me when I was a kid, before I even knew about programming. So why Ruby? There are a lot of things that are implemented just a little bit different in each game. And it's really common to have to customize your tools on a per-game basis. So it's not like you can just download something off the internet using an off-the-shelf tool. You're going to have to create something that you need to maintain. And I don't know about you, but when it comes to maintaining code, I want to do it in Ruby. And so when I started using Ruby, I switched over all of my tools to being implemented in Ruby. So when I had to make customizations, I was doing it in a language that I really loved using. So we're going to start looking at the methods by which you can interact with a game in a new way. We're going to start with relative searching. And this is important because when you're looking at these old games, oftentimes the character sets that you're working with, in fact, in almost every case, they're not what you think. They're not like ASCII or Shift-JIS or certainly not UTF-8. They're some proprietary thing. It's not even standard on the Famicom. It's different for each game. And so before you can break into any of the textual data that's in a game, you have to crack that character set. And one of the best ways to do that is relative searching. I'll show you what I mean. This is the game that we were looking at before. And we see the characters there, otsukare no, in this dialogue, okay? And that is an open door for us. The reason it's an open door is that those characters in almost every 8-bit character set are in the same position relative to one another. A, I, U, E, O, ka, ki, ku, ke, ko, sashi, su, se, so. They're incremental in that sequence. It's not true in UTF-8, but what we're able to do is assign to each of those characters an imaginary incremental value. A, I, U, E, O, ka, ki, ku, ke, ko. And these characters, it's almost a sure bet they'll be in that incremental order in an 8-bit character set. Not true for UTF-8. However, the same is not true for ga, pa, kya, o, n. They tend to be placed in different places in the character set for whatever reason, obviously. So don't try to relative search with those. So here's what we do. We take those imaginary values and we plot the values for a string that you want to find. Mina konnichiwa. And you then evaluate the difference. You see how those numbers relate to each other and calculate the difference. And that is the relative signature of the characters that you want to search for. So regardless of what the actual values are for those characters in the character set, the relative signature of that series of characters is going to be the same no matter what. And that's what a relative search is for. But if you tried to do this without some sort of tool, it would be impossible. It would be so difficult, so time-consuming. So let's Ruby. Relative search in Ruby. We want a relative search tool that runs on the command line, and we want it to be easy to distribute and install. We want it to run as a command on the command line, like I just said, and we want it to be able to search very large files, like even N64 games or something like that, without loading them into memory entirely. And this is the interface that we want for a command line tool. So ARS is a relative search. Don't try to pronounce it. And you can specify the file and the string of Japanese characters that you would like to relative search for. So we're going to spin up a Ruby gem to meet that interface really quick. So we'll bundle gem ARS. It'll create our Ruby gem. We'll go in. We'll make a bin directory. We'll stub out an executable. We'll make it executable. And then we're going to bust open our IDE. We'll stub out, like I'm not proud, this is really simple so that we can all understand it very quickly. There's not much object orientation or anything here. So we'll go ahead and stub out that executable file, parse the arguments, and then find in the ROM the kana that were specified on the command line. When we parse the arguments, there's a lot to this, but a great way to do it is with option parser. So we'll specify a new struct that has the attributes that we want to be able to specify on the command line. Scratch English, that's for a future version. And then we create an option parser, set a banner, a separator, this stuff will print out on the command line. And then we specify the options. Don't worry too much about the syntax, you can look at the slides later, so we'll fly through this. But the concepts are that there are tools that make it very easy to make these command line tools. So the option parser will look for a ROM file that the user specifies on the command line, and it will also look for the kana string. It will print out a separator for some more common options like help, and then there's another one for version. And then once it's done that, it'll parse the arguments off the command line. So unless the person has specified a ROM and the kana, it will print out the option parser, which will show the help documentation, and exit. Otherwise, it returns the option. OK, so now we've parsed. We're done. We're done with parsing. So let's generate those imaginary values on the fly. Really easy. Put them all in an array, and then seek them by index. So basically, you want the imaginary value for character, go to the kana order table, and look up the index of that character. I'm highlighting anything that we're going to use in a future method, so you can just kind of remember how it's implemented and then make reference to it later. So imaginary values for an entire string, we split the string, and then we get the imaginary value for each character in the string. If we want to get the signature of a series of bytes, just a random series of bytes, it could be the thing that we specified on the command line, but it's also going to be every chunk of data that we pull out of the ROM to compare against it. The relative signature of the first character is always going to be 0, because it was relative to nothing. So it's 0. And then we keep track of the previous byte and compare it to the next byte. So for each byte, except for the first byte, we take the current byte and subtract the previous byte from it. And that's the difference. We add that to the signature, and then we return the signature when we're done with all of the bytes. So in our tool, we'll trigger the calculations in a find method. We'll grab the imaginary values. We'll grab the signature of the input. And then we'll grab the file, figure out how big it is, set up a progress bar so we have a very pretty experience while we're waiting for it. On a large file, it can take a long time. And then you work your way through the file byte by byte, incrementing the bar and reading. This is the important bit. This is really actually the important bit for this type of tooling. You read the file and seek to the offset. Rather than reading the whole file into memory, you seek the offset with the file handle, and you read just enough bytes to compare with the signature that you have from the command line. You unpack that data, and so that's the method that you need to use in order to do this in Ruby. You unpack that data as a series of bytes using that syntax, and then you can get the signature of the bytes and compare it to the signature of the input. If we have a match, we report it, and this is how we do it. We get the location. This is a helpful method to know when you're working with binary data. Oftentimes, you'll want to output offsets as hexadecimal because it's easier to work with rather than decimal. And so in order to do that, we take the offset and we cast it to a string. It's an integer, or a fixed num, and we cast it to a string, but we specify that we want it in base 16. And that'll give you a hexadecimal output. And then you upcase it because I'm picky like that. So each of those bytes, we also want to just go ahead and print them out as hexadecimal so that the user on the command line knows what the values were. Not the imaginary values, but the concrete, like the actual values. And then we log that out using our progress bar gem. OK, so this is what it looks like. We do a rake install, ARS. It gives us the usage. But let's take it for a spin for real. Here we go. That doesn't look quite as good on. What are we doing here? All right, so we'll just run it like that. All right, and it found a match. I'm going to run it again as I get my power adapter. Enjoy the progress bar. Oh, feedback. Sorry about that. So we have a match. Let's take a look at it. This is the data that we found. And it found a match right here with these bytes. And using that knowledge, we can extrapolate out this one here. But there's so many other data, like so many other bytes that we don't know. So what do we do with those? Well, we now have the concrete. We can go back to the game, look at the rest of it, and kind of from context fill out the rest for those ones, right? So now we know. We have, but this still isn't the whole alphabet. It's just a subset. So what do? Well, there is another way. what if I take my hex editor and I start doing this? Eight zero, 8 1, 8 2, 8 3, 8 4, 8 5, and then I go back to the game and re-execute it. I have a known exploit into the game now. I know it's going to print that string when I talk to Oji-san. Oh, Antonio, sorry. But now it's not going to print out his text. Antonio's gone. My exploit is in there. And it's going to print out the characters that correspond, or behaviors in the scripting language that correspond to each of those bytes. And now I have a complete table. And we need a way to store those findings for use in other tools. So we use a table file. And so now we have a mapping of the whole alphabet and control characters, because I was able to go in and brute force the character set. That's relative searching. So what do you do with a table file? Well, I know what a lot of us English speakers do. We start dumping scripts. Why? Because I gotta send it to a translator. So let's look at script dumping. Now that we have a table file, what would it take to dump the script for the translation? Not very much. And the reason is we've already created a tool that goes over, it takes the command line arguments and then goes through the file byte by byte. So now all we have to do is cross-reference each byte with the table file to determine what should be dumped. And allow the command line user to limit the scope of the dumping. Maybe allow them to specify a file to write out to instead of using standard out. So we're already not far. We load the table like so. Line by line, it's an ASCII file, so you can do this. Just line by line. You split it on the equal sign, and then you make the new line characters that the user has put in there in code actual new line characters, and then you just return all of those values. The keys in our table file hash, they're printable hex strings straight from the table file. So one thing that will also be helpful for us to do in our script dumper is be able to get the hex strings for a bunch of data so that we can pull binary data, convert it to these ASCII keys, and then look it up in the table file so that we can output whatever the hiragana, katakana, or control behaviors are. And so we can do that with that code right there. So what else could we use? Well, I mean, that's a legit script dumper right there, pretty much. Like with the stuff that we've already talked about, you've got all the tools to go and start dumping scripts from games. Adding support for multiple byte table values is really easy. Dump strings by dereferencing the pointer table. We'll talk about what that is in a second. But these are features that people would want in a tool that you could implement because you don't mind maintaining your tool because it's written in Ruby. A handful of games require multiple table files with control characters that go back and forth. Again, you're customizing on a per game basis. So converting those printable hex back into writable data is valuable as well. And you can do that by taking the printable hex, joining them into a single string, and then calling pack on it, which is the opposite of unpack. And then also you can convert a 16-bit pointer to 2 little Indian bytes. I'll show you why we need to do that in a second. Writing those 2 bytes back as a pointer into the ROM. These slides are out of order. Sorry. Converting arrays or strings of values into binary data. I'm not sure if we'll have to come back or if they're just duplicates. But just really quickly, before we get to that, about the script reinsertion, I want to talk about assembly hacking really quick. Code disassembly is basically the same thing as script dumping. The difference is we don't need a table file because the translation from bytecode to assembler is the same across all games. That's the difference. So you can use off-the-shelf tools for that. So code disassembly is the same thing. You're looking at the bytes and you think, what do they mean? Well, in this case, they kind of break down like that. The rest is garbage. I don't even know what it is. But this is a routine I wrote like 8 years ago. And it translates into these assembler codes. So you can just grab, again, it's all data. So you can then dump that into a file, make modifications, and change behavior. And there are some common situations where manipulating the disassembled code can be really useful that we'll talk about later. All right, so script translation. Ruby can't help you do that. So you just have to find somebody who can translate your script for you. I can't. So I have a friend named Tom who lives here in Japan who helps me with it. You're the best, Tom. All right, so really quickly, we're going to talk about graphics. Actually, let's skip over this. This is pretty complicated, and I wanted to touch on it so that you could see the way that all things are data. If you're interested in this, rather than explaining it now while time is short, feel free to look at the slides afterwards. But you can see how the data, each one of those bytes converts into a binary representation for its part of the graphic. And then you add those together, and it creates one of the 4 colors in the palette. So that's how graphics data worked on the NES. It's really simple. So those bytes there equal this sort of, if you squint your eyes really hard, it's kind of like ah. And even the palette itself is defined by data, right? So everything's data. You can change everything. So why not use Ruby for this? Because it doesn't change from game to game. So you don't really need to customize the tools. Just use something off the shelf. So let's talk about script insertion. It's just the opposite of extraction, right? You replace Japanese alphabet graphics with English graphics, and you update the table file, and then you convert the translation back into binary data and insert it back into the ROM. Well, wait. There's a problem. And this is the problem. The end bytes there will not line up with the new data that you're inserting. And so people's text will get cut off midstream, and it won't load from the right place. You have to go to the pointer table and update these values, which point to these values. And when you update them, you can point to the new strings that are of different size. You must update the pointer tables. It's pretty trivial. And those were the little code samples. We don't have time to go over them, but they're there. They'll show you basically how to recompress and order the bytes properly so you can get them into a binary file. The trick with it all is Little Endian. So the 100 is actually 001 in code. And those were the code samples. So you can look over those. And then I've got to run because we're at 11:30. So there is one more problem. It relates to script size. And for that, we use dual tile encoding. It's an assembler hack where we take what was for Japanese and use it for English. There's substring compression as well. It's similar to DTE. It requires assembler hacking as well, but it supports more than 2 characters. So we're wrapping up here. The improved script insertion, it's actually more complicated than you think, but that's why you want to maintain it in Ruby, because you'll have to add these things basically on a per game basis. And so you want to be doing it in a language that you love. That's why we want to use Ruby. So with that, if there was anything you wanted to go over, feel free to hit me up over the rest of the day. I love talking about this stuff. Or you can hit me up on Twitter or email. Thank you so much.